Hello, my name is Brian Dyck. I'm a software engineer, and this is my YouTube tutorial series where I work on HackerRank challenge problems. This challenge problem was sent to me by a viewer that was wondering if I could help them solve this problem. So this is called the time complexity recursion problem, and it is as follows. Given t queries n1 through nt, counting only plus, minus, times, division, module, greater than, less than, equal to, less than equal to, greater than equal to. Determine the exact number of basic operations that would be performed when the following function foo is invoked on each value of n sub I. And then it gives us our definitions, some basic information about input format, constraints, output format, and then a sample input, sample output, and an explanation. So that's all pretty standard stuff. I'm going to go ahead and go straight into looking at these two functions. Oh yeah, by the way, this is our first video in Python. Python is not my favorite language. I find it horribly and grossly inefficient, but hey, he wanted it in Python, he gets it in Python. We will work with him. So basically, we've got this function foo here. Foo has four different cases. We have when n is equal to 0 case, we just return 0. So this is basically a base case. Then we have a elif. We check to see if it's a number divisible by 3. If it is, we have the set of functions that we return. Then we have another elif to see if the remainder is just 1. And then we have an else statement that covers everything else. So basically, when you look at a problem like this, the first thing you want to see is you want to find whatever patterns or similarities you can find within this problem. See if there's a quick cheat way of solving it. If there's not, the next thing you can do is you can look at breaking down case by case, what makes each case special, what makes them similar. How can you make this less confusing to understand? And to really figure that out, you kind of need to start just by plugging in some simple values that are pretty common. So let's look at foo as in, and let's describe foo as the num of operations just for n. Number of operations for n. So meaning I'm going to describe foo in terms of the number of operations that would happen in the actual foo function. So let's say when n is equal to 0, we obviously just return 1. So there is only the one operation. It's the operation to check if n is equal to 0, right? When n is equal to 1, we now have a remainder of 1. So we would have gone through this check. This is not it. So that's one function or one operation. We then have this elif. That's a modulus operation. That's 1. Another equals. That's 2. So that's a total of 3 so far. Then we go down to this elif. We have another modulus, another equals. So that's 5. Then we have this foo function where we do n minus 1. That minus is 6. And then we have our v plus var, so that's 7. So that's 7 operators and 2 function calls. So that's 7 plus however many function call or operators are called in foo of n minus 1 plus however many function calls are called in bar of just n. So here, if we plugged in the number 1, which is what we have, that would be 0. Foo of 0. We know foo of 0 is 1, so we get 1. So that's just evaluated to 1. Bar of n, when bar of 1 is called, we have count is equal to 0, and then we return count. Nothing else gets ran because it's outside of the range of 2. So we would just return 0, and then this would have 0 operations. So the total number here would be equal to 8. And I'm just going to zoom out just a little bit. There we go. That works. Hopefully. Let's see. There we go. We got it now. So now we are going to look at n is equal to 2. Another example. So when n is equal to 2, we now have a remainder of 1. So we have gone all the way down here, 1, 2, 3, 4, 5. And then we have this foo function with a minus in it. That's, oops. Wait, no, we don't have a remainder 2. We have a remainder 1. So we go through all of this. So 1, 2, 3, 4, 5. Then we go into the else statement. Sorry. We call foo with n minus 2 plus foo of another n minus 2. So that's 6, 7, and 8. And we have this return v plus 1. And that's 9. So there's 9. So in this case, we have 9 plus foo of n minus 2 times 2. And that's our solution for n is equal to 2. We put into here, we get foo of 0. Foo of 0 is 1. So 1 times 2, that's 2. That equals 11. So that would be our n equals 2 case. Next, we have when n is equal to 3. So when n is equal to 3, we have 1, 2, 3. We go inside of here. We have this foo divided by 3, so that's 4. And then we have 4 I in range n. So that means this is going to run n times. So let's see what's inside. We just have a simple plus. So that means it's going to run n times. So that would just be n more operations plus whatever that foo results in. So that would be 4 plus n plus foo of n integer division by 3. So in that case, in this case here, we have 4 plus 3, which is 7, plus foo of 3 divided by 3, which is 1. So foo of 1, that equals 8. So this is 8 plus 4 plus 3, which is equal to 15. Boom. So these are our basic 4 cases that we could have. We're either 0, where we just return 1. We have a remainder of 1 after dividing by 3. So that would be 7 plus foo of n minus 1 plus bar of n is equal to 8. Then we're an else statement. Else is going to just be 9 plus foo of n minus 2 times 2. And then we have this n is equal to 3, 4 plus n. When it's divisible by 3, it's 4 plus n plus foo of n divided by 3. So these are really nice functions that we can define if these functions returned the number of operations to get to that point. Unfortunately, they do not. But we can always write a function that does that. So let's just copy and paste these definitions so we can easily keep track of what these are doing. We'll just paste them above the definitions for count operations. Paste there. And then first, count operations, this is what we're actually supposed to be writing. And what we're going to do is we're just going to define a range, or sorry, not range, a result is equal to a new list for n in samples. We are going to append to result dot append foo of n, and then at the very end we return that result. Okay, so now what we want to do is we want to modify this foo function for each of our cases. So n is equal to 0 is already done for us. It just returns 1. Then we have our elif n is divisible by 3 case. In this case, remember, we should be returning 4 plus n plus foo of 3 divided by n. So that can replace all of this, and now we are returning the number of operations it takes for that n. Then in this elif, if there's a remainder of 1, then we are going to be calling I think it's 7 plus foo of n minus 1 plus bar of n. Now let's just double check that one from the notepad. Yeah, that's correct. So then our else case, we have our 9 operations that are automatically done, plus foo of n minus 2 times 2. All right, so that's very nice and neat. Let's try running this and see if it works. So let's run code, and it fails. Okay, so this looks right, this looks right, this looks right, this looks right. The one that failed is 4. Interesting. So in the case of 4, let's go ahead and write it out. So n is equal to 4. We take, in this case, we have a remainder of 1 after dividing by 3. So we'd go into the same case as 2. So we would have 9. Oh, wait. No, or sorry, we'd have the same case as 1. Sorry. 9 plus, or 7 plus foo of n minus 1 plus bar of n. So in this case, foo minus 1, n minus 1 is 3. So we'd have 15 subbed in here. That's 22. So we'd have 22 plus bar of n. And what does bar do? Oh, we didn't implement this at all. Of course it's not going to run. Okay, so let's look at what bar does. So bar has an outer and an inner for loop, and then inside of here we have a single if statement with 2 operations. And then regardless of result, we're doing an additional operation, either plus or minus. We can get rid of this part, and we can just simply say count is equal to count plus 3, because that's what effectively is happening. Now we should be able to run this. And congratulations, you passed the sample test. Everything's working fine. Let's go ahead and submit this code. And it's running. It's running. And it is lighting up wrong all over the place. Uh-oh, we did something wrong. Let's see here. What did we do wrong? Issue. We have 3 divided by n instead of n divided by 3. Silly mistakes like that can throw off a lot of stuff. Let's run code again. There we go. Pass these test cases. Now we can submit our code. Passes all these right away. Success is success. And these are taking a little bit. Let's see. We got hit with the red clock outs. So we terminated due to timeout. No problem. Let's just go back and let's see where our code is inefficient. So looking at this, there's not really a lot we can do with this to speed this part up. This is as efficient as it's going to get as far as simplicity's sake. These are all just simple one-line return statements that go back and then have the recursive calls occur. Now, on the other hand, Mr. Bar up here, this has 2 loops, an outer and inner loop, to count up the number of counts from bar. This is where the issue with our time efficiencies coming in is with these loops. We want to get rid of them. So to get rid of them, we're going to have to think of a clever solution because we don't really know how to get rid of that yet. Let's do a bar. We want to make sure we're returning the number of operations it takes. And it's also good to note that this is only being called on the numbers 1, 4, 7, 10, and then so on and so forth. And what's really interesting when you note this, at 1, the answer is 0. At 4, the correct answer is 9. At 7, it is going to be, well, let's run through it with 7. So with 7, we have 7 in for the k. So we do from 2 to k, 2 decay would be starting off with 1. So that would be one of these loops. And then we have 3, 2 more. So that's 1 plus 2. And we have 3 more, 1 plus 2 plus 3. 4 more, 1 plus 2 plus 3 plus 4. 5 more, 1 plus 2 plus 3 plus... Oh, you know what? This is a series where we end up with 1 plus 2 plus 3 plus 4 ... to plus n. Right? So we can actually super simplify this by using some nice little series maths. So we could define, since this range here is from 2 to k, and then we start at 1 always and go up to our ith value. This could be defined as we could define n is equal to k minus 2. And then we could use this little piece here, n times n plus 1 divided by 2. And this will get us the total number of these inner loops we get. And then we just need to multiply that by 3. And then that gives us our actual number of operations that we would have had. So we can get rid of our for loop with this constant timeline, which is very nice. Control X, Control V, and we don't even need to count. So yeah, that's a much nicer way of solving this part, and that will speed us up tremendously because now we have no iteration. It's all just that simple recursive call and then a constant time on bar. So we pass our test cases still, and then we can submit our code. And once we submit our code, we will see everything light up. Test case 8 is being a little stubborn, but it'll come through. There we go. And we now have all of our test case passing way faster. Before, these were taking over 10 seconds. Now these are happening in less than, that's like what, 1/20th of a second? So much, much better time than we had before. So yeah, if you like this video, make sure you give it a thumbs up. If you have requests for other types of HackerRank challenges or other problems that you'd like solved, go ahead and leave them in the comment section below. If you want to see more of this content, make sure you subscribe and hit the bell notification. I will also be continuing my HackerRank interview preparation series. I took a little bit of a hiatus from it because I was moving and changed jobs and such. So I will be getting back into that shortly. And yeah, thanks for watching. Be sure you comment, like, and subscribe, and I'll see you next time. Bye.